In section 7.7, we're going to be looking at approximate integration here. So the question I want to start with is, what's the definite integral of e to the negative x squared with respect to x? So none of our basic methods will work on this. Substitution doesn't work, trig integrals, trig substitutions, partial fractions, integration by parts, none of it works. However, this is a definite integral, and remember that definite integrals are the area underneath the curve. And remember that when we defined the definite integral, what we did was we took an approximating sum of areas of rectangles. The base of the rectangle was delta x, that is our base, and then the height of the rectangle was f at some x value. So for the kth rectangle, we call that x sub k star. So that is our height. And we're adding up height times base for a bunch of approximating rectangles. And then we're taking a limit as our delta x, our width of a rectangle, approaches 0, which is going to make n, the number of rectangles, approach infinity. So lots of times we'll take this x sub k star to be the left endpoint or the right endpoint or the midpoint. Those are the most common choices. Now this will simplify a little bit here. The integral, definite integral, is equal to the limit of that, but if we take off the limit, then it'll be approximately equal to this finite sum of height times base. And then the base is a constant, so that'll factor out of sum. So we got that delta x out in front. That's our b minus a over n. And then times the sum of the function values. So this is a nice starting place to approximate definite integrals. So let's say we want to estimate integral from 0 to 1 e to the negative x squared dx graphically and then also numerically with n equal 2. Using the following method. So first, the left-hand rule. So for the left-hand rule, you use the left-hand side to get your heights of rectangles. So the formula for the left-hand rule is delta x, that's our b minus a over n, in this case n is 2, times the sum of our function values, f of x0 up to f of xn minus 1. So let me show you a quick example with Wolfram demonstrations to show you how this could work with sine x here. So here I've got n equals 4. I'm using a left-hand sum. So the blue area is the area underneath the sine x curve, and this is just from 0 to 2. And I'm going to approximate that with 4 rectangles. So the base of my first rectangle, first of all, my delta x is 2 divided by 4, which is 1/2. So there's my 1/2 base. I use the left-hand side of that base to get the height. So no rectangle there. However, in this second rectangle, I use the 0.5, go up to the function to get the height. And we can see the height of that rectangle, it's approximately, looks like it might be 0.4647, something like that. And then we know the base is 1/2. So we can estimate the area of that. And then the base here again is 1/2. We take 1, plug it into the sine function. So this height of this rectangle here is sine of 1. And we could approximate that graphically or put it in the function to get a more precise value. But that looks like that's about, I don't know, about 0.86 or something like that, 0.87. And then our fourth rectangle, base is 1/2. We put 1.5 into the function to get the height. So that's this area here, and it looks like that height is pretty close to 1. And then Wolfram has actually added up the areas of those rectangles. So our approximate area is 1.15920, and then the exact area to 5 decimal places is 1.41615. And our error there is going to be 0.257. So you would subtract these two values. So well, let's do that with this function here. So we're using n equals 2. Our b is 1. So this is our b. This is our a. And so our delta x here is going to be equal to 1 minus 0 and then divide by 2. So that's 1/2 or 0.5. So I've got a first base which is right here, and a second base here. I'm using the left-hand rule, so I use the left-hand side 0, go up to the graph of the function. That determines the height of my first rectangle. So that rectangle is going to look like this. And then at 0.5 to 1, that's the base of my second rectangle. I'm doing a left-hand rule, so I use 0.5 to get the height. So that height's going to be right here. So that second rectangle is going to look like this. So I can approximate my integral. So my integral from 0 to 1 of e to the negative x squared dx. Graphically, I can add up base times height for the two rectangles. So I can approximate my function values. I've got the delta x exactly, that's 0.5. And then the first height is the function value at this, which is 1, so the function value at 0. And then the second height is the function value at 0.5, which looks like that is approximately, maybe 0.77. So we've got 0.5 times 1.77. Let's go ahead and compute that on the calculator. So 0.5 times 1.77, about 0.885 approximately. And again, that 1 is f of 1. And the 0.7 is f at, let's say, I'm sorry, it's f at 0. And the 0.7 was the function value at 0.5. So my x0 is 0, and my x1, which is xn minus 1, is 0.5. So we can approximate this a little bit more closely because we actually know the equation of the function. So if we want to do this numerically, we can take and plug those function values into the equation. So we're still using this. This is going to be our delta x, 0.5, and then times f at 0. Okay, that is my a is my x0, and this is going to be my x1, and my b is going to be x2, which doesn't get used with the left-hand rule. So f of 0 plus the second height is the function value at 0.5. So f at 0.5. And that's going to be 0.5 times f at 0. Here's our function f. So we plug in 0 e to the negative of 0 squared plus f at 0.5 e to the negative of 0.5 squared. And that'll give us a better estimate. So let's go ahead and plug those in. So I got my 0.5 outside, parentheses. I'm going to use the second function of the natural log to get my e. And I've got a negative of 0, and that guy gets squared. Going to arrow to the right, and then plus, same thing, with a 0.5 there. So I'm going to do second function of the natural log. And I've got a minus sign and 0.5, and that guy gets squared. Arrow to the right, close up the parentheses, 0.8894 to 4 decimal places. So closer to 0.89, and here 0.885 rounds to 0.89. So this is graphically, you're just getting the heights from the graph. And this is numerically. You're plugging in the values into the equation of the function to get the heights. So if they just give you a graph and they don't give you a function equation, you can do this, estimate the heights of your rectangles. If they actually give you an equation of the function here, then you can plug values in.